Thank you. Okay, everybody, and welcome to this week's lecture. It's going to be non-commutative generalized Riemann hypothesis. So by Gonçalo Tabuada, if that's okay. I should have checked this beforehand.
That's fine.
Yeah, please. Okay, so.
Okay, thank you so much for the invitation. It's a great pleasure to be here virtually. As I was saying, I mean, I've never been in Prague, but I always heard great things, and I hope that one day I'll be able to visit you guys. Yeah, so my talk will be, this is the title, and the point is pretty simple. I'm just going to explain the words in the title. That will take half of the talk, and then the second half, I will provide an application to commutative geometry, and then an application to non-commutative geometry. Okay, so the first word in the title is Riemann and Riemann hypothesis. So I'll use that pretty often. So let me just denote by RH, that will always stand for Riemann hypothesis. And also I will use the word non-commutative very often. So NC will stand for non-commutative. And please interrupt me to make things a little bit more interactive. So how everything starts it with the famous zeta function, which is defined by this Dirichlet series. So S, it's a complex variable. And what do we know about this function? We know several things. We know that this function, it actually converges absolutely in this half plane when the real part of S is greater than 1. This was proven by Riemann. We know that we have a Euler product description of this function, so we can write it as a product over all prime numbers of 1 over 1 minus P minus S. This all again in this half plane region. This was proven by Euler 100 years before. Then Riemann also proved that this zeta function actually admits a meromorphic continuation. To C, to the entire complex plane, and it actually has a pole which is simple at S equal 1. So if we want to draw a picture of this, we can say, well, we have something like this. So here we have 0, and here we have 1. And the function is well defined in this half plane region. Here it's 0, here it's 1. It admits a meromorphic continuation to C, and it has a single pole here. And then what is really the Riemann hypothesis, this very famous Riemann hypothesis, it comes from 2 centuries ago. It says the following, that if you have a 0 of your function, and if this 0, it's in this critical stripe, in other words, if its real part is between 0 and 1, then it actually, the real part of this 0, it's 1/2. So if you want, in terms of a picture, this is simply saying that, well, the zeros in this region, if they exist, they are necessarily in this vertical red line. The function has other zeros, which are called trivial zeros, which are in this negative even integers. But those in this critical stripe need necessarily to be in this vertical line. This is very famous. Everybody heard about this. And Riemann was able actually to relate this Riemann hypothesis with the distribution of prime numbers. So that was his main motivation. So let me now move on in the title, explain what is the generalized Riemann hypothesis. So the generalized Riemann hypothesis has 3 ingredients. So we'll be working over a global field. So little k will be the global field. We'll be working with a smooth proper scheme. and we'll choose an integer w between 0 and twice the dimension of my scheme. And now, using these three ingredients, we'll be able to define the associated L function. And from there, we consider the generalized Riemann hypothesis. But in order to define this L function, I need some notations, which are quite important, which are the following. So if you have a global field, so let me just recall you that a global field, by definition, it's necessarily a finite extension of Q, so what is called a number field in the case of characteristic 0, or in the case of positive characteristic, it's actually a finite extension of this fields of rational functions in one variable over a field of over a finite field. Okay. And then following Serre, we denote by sigma little k. So this infinite set, so it's infinite, this infinite set of non-Archimedean places, of non-Archimedean places, of the field. So this, you can think about this as absolute values up to equivalence, all possible absolute values that you can define on your field up to equivalence. And then if you have one of those, a nu, then you can consider several constructions. So you can look at the completion of your field. So the completion of your field at this place. You can look at the associated valuation ring. This associated valuation ring of this completion. You can look at this, I'll write it like this, to the associated residue field of this valuation ring. P nu will denote the characteristic of this residue field, which will be a finite field. And so if it's a finite field, we can also talk about its cardinality of this residue field. So maybe an example, just to give an idea, what are those things? So suppose that we are actually over Q, then the set of non-Archimedean places, it's in correspondence with the prime numbers. And so if I choose a prime number, this will give rise, the completion will be the p-adic numbers. This will be the p-adic integers. This will be z mod p. This will be the characteristic, which will p, and the cardinality, which will also be p. Okay. And then just another ingredient is that when you look at the absolute Galois group of this completion, it maps canonically to the absolute Galois group of this residue field. And then this is surjective. It comes, so you can consider the kernel, and the kernel is what is called this inertia subgroup. So this is a finite field on the right. So if it's a finite field, means that its absolute Galois group, it's necessarily z hat. And in z hat, you have a canonical element that are arithmetic Frobenians. So if you have an element, you can raise it to n nu. So this, it's an element in here, which is actually a topological generator of this group. And then I'm interested not in this element, but actually in its inverse. So in the inverse of this one, which will denote by pi nu, which is called the geometric Frobenius. Okay, and one very last thing is that in order to define these L functions, we make a choice. We choose two things. So we choose a prime number different from the characteristic, and this for every place. And also we choose an embedding, iota nu, from this completion towards C. Okay. Good. So these are the ingredients that we need to make the following definition, which goes back to Serre. It's the following. So we have this definition of Serre. From the L function of this weight, of weight W, So you define it as a infinite product over all non-Archimedean places of these L functions, the corresponding non-Archimedean factors. And so how are those things defined? So you define these functions here as follows. So you can look at the étale cohomology W, because I'm considering W, of my X. So I need to base change from K to the completion. And then I want to consider things that are geometric. In other words, I go from there to the separable closure. And I consider it with QL L mu coefficients. So this, it's a vector space. And I consider those things that are fixed under this inertia subgroup. So those things that are fixed under this inertia subgroup will carry an action of z hat. So there's z hat acting there. So the geometric Frobenius will act there. So I can look at the geometric Frobenius acting here. So it's this element. And now what I want to do is to take the characteristic polynomial of this action, of this automorphism. But then I want to replace t in this polynomial by the cardinality here, and then raised to minus s. So in order to do that, I need the coefficients of the polynomial to be actual complex numbers. So I need to first to base change this from to c. So I really need to base change this to c first, and using this embedding that I've chosen. And then I take the characteristic polynomial, and then I replace t by the cardinality minus s, so identity minus, and take the determinant. So this is my factor at this specific place, and then I do the product over all places. And this theorem of Serre says the following, says that actually this L function of this weight, weight W, it converges absolutely when, so in this half plane region, when the real part is greater than W over 2 plus 1. Okay, so now see, we know that in the case of the zeta function, so Riemann proved that you actually have a meromorphic continuation to the entire complex plane. In general, that is not known. So those are conditions that are pretty standard and people are interested in. So the first one is that actually this function here admits a meromorphic continuation, admits a meromorphic continuation to C. And second is that actually, and is something only in characteristic 0, is that the only possible pole of this L function, it's actually is located at this point, so it's S equal W over 2 plus 1, and with W being an even number. Okay, so those conditions are known in many cases. So for example, in characteristic 0, they are known for elliptic curves, for certain abelian varieties, for certain Shimura varieties, etc. And in positive characteristic, so there's only condition 1 in positive characteristic, and that's actually a theorem of Grothendieck. It follows from the work of Grothendieck. It's a result. Okay, so what can we say here if we want to draw this as before? So we have this this function which is well defined in this half plane region. So it's well defined in this half plane region thanks to Serre, thanks to the result of Serre. Okay, so here it's 0. And now, assuming condition 1, that you actually have meromorphic continuation, then you can talk about the generalized Riemann hypothesis, and which I will write by R W of your X. So it says the following. So if you have a zero of this function, and this zero is in the critical stripe, in other words, if it's here, then that implies that the real part of that zero needs actually to be here. So geometrically, if you want, so geometrically, this is saying that your zeros need actually to be here, where, so let me write it. So where here it's w over 2, and here it's w plus 1 over 2. So the zeros that exist in this critical stripe need necessarily to be in this vertical red line. And why is this generalization of the classical Riemann hypothesis? Well, the Riemann hypothesis is really the baby case. So it's the case where the base field is Q, where your algebraic variety is just the spec of K, of Q in this case. And here there's no room for this integer, it's necessarily 0. So when you do this, the L function that you get in this particular case, it's actually the zeta function. So in other words, what this generalized Riemann hypothesis, it degenerates to the Riemann hypothesis. Okay, so it's really the baby case. And then if you go a little bit, so suppose that now it's just a finite extension of Q. So suppose that it's a number field. And you take for algebraic variety the spec of Q. And here again, there's no room for integers, it needs to be 0 because the dimension is 0. Then in this case, the L function that I've just defined in this particular case, it actually reduces to the what is called the Dedekind zeta function. So it's a sum over all integers in the over all ideals in the ring of integers of your number field, and you do 1 minus 1 over the norm of your ideal S. So it's really a generalization of the zeta function. And in this case, the conjecture is what is called the extended Riemann hypothesis. And since I'm over K, let's specify the K here. Okay. And finally, so we have this big conjecture, this huge conjecture, and what is its status? So the status of the generalized Riemann hypothesis. Well, as you expect, in characteristic 0, no cases are known. No cases are known. So it's completely open, of course, because you see that even the simplest case is just the Riemann hypothesis. Okay, but in contrast, if you go to positive characteristic, then it's actually a theorem. It was proved by the Ling, by connecting the work of the Ling on one side with the work of Grothendieck on the other. Okay, so it's really a complete different picture depending on the characteristic.
And okay, so this, sorry, these are the Weil conjectures you're talking about.
Yeah, the Weil conjectures are over a finite field, and then in the Weil 2 paper, so that was Weil 1 of the Ling, then he wrote a Weil 2 where he defined this formalism of L-adic sheaves. And using this formalism, you can actually prove the characteristic 0 case, because you can think about this as being an L-adic sheaf over a curve when you are working over a field of characteristic 0. So when you are over a function field, let me go back here. If you have a global field in positive characteristic, it's a finite extension of this one. So it's actually given by a function field of a curve. So you can do things over that specific curve, and so you can consider this L function as the L function of a certain L-adic sheaf on that curve. And then using the result over finite fields, he can bootstrap his result to the case of L-adic sheaves over a curve. So that's how the Ling proved it. And the meromorphic continuation was proved previously by Grothendieck already. Okay, so this is more or less my introduction. And now let's move on. Let's try to explain what do I mean by non-commutative geometry. So this non-commutative geometry means different things for different people. So here I mean non-commutative algebraic geometry. So it's a subject that was started by Manin in Moscow and many others. And so let's say that I'm just over a field, it's completely general. I start with the following definition, something that goes back to Bondal and Kapranov, which is the definition of a differential graded category, so DG category. So this is simply a category which is enriched over complexes of k-vector spaces. So it's ordinary category, but the Homs are not sets, are complexes. Well, so if you have an algebra, or if you have more generally a differential graded algebra, then this gives rise to a DG category with a single object where the endomorphisms is that DG algebra or algebra. So you can also think about a DG category as a DG algebra with several objects if you want. And so everything that comes from algebra gives rise to DG category, and also everything that comes from geometry. If you have a scheme, then you can look at the perfect complexes on that scheme. So these are complexes that locally they are quasi-isomorphic to complexes of vector bundles that are bounded. And this carries a canonical differential graded enhancement, so also gives rise to a DG category. So it's a world where you can do algebra and geometry simultaneously, okay? So let me see.
Sorry, can I ask another question? So why are you enriching over complexes and not over DG algebras?
No, you need to enrich it over a monoidal category.
Okay.
And you consider the monoidal category where you are enriching, it's the category of complexes. The category of algebras are the algebra or are the algebra groups or the algebra objects in that category.
Okay.
So maybe let's say in a different way. Algebra, a DG algebra is a DG category with a single object. So everything what I'm going to say about DG algebras, you can think that I'm just talking about, everything that I'm going to say about DG categories, in your mind, you can just think that I'm talking about algebras. It's just the case where there's a single object, okay?
Okay,
so it's everything that you are used to with algebras makes sense in this generality. Just a slight generalization where instead of an object, you have several ones. So you have several DG algebras and morphisms between them. It's more or less a DG category. Okay, so this famous example of Beilinson says the following. So if you look at the projective line, so the category of sheaves on projective line, it's very different from a category of modules over an algebra. But if you go to this drive setting, if you take these perfect complexes, then this turns out to be Morita equivalent to an algebra, but it's a non-commutative one. So it's this algebra of matrices of this shape. So you see the projective line, which is something which is not affine, in this world becomes affine, given by an algebra, but a non-commutative algebra, okay? And then I'm interested not in this generality, I'm interested in a particular class of DG categories, which was defined by Orlov. So if you have a DG category, let me just use this notation, the DG category A. Okay, so a DG category A is called non-commutative, so a geometric non-commutative scheme. Geometric non-commutative scheme if there exists a smooth and proper scheme X such that your category, it's actually inside this category and in something that is called admissible. So it's a bit technical, means that it actually admits a left and right adjoint. So these categories are those pieces that are inside the categories of schemes, of ordinary schemes. Okay, it's interesting because there are pieces that are not actually schemes that live inside. So let me give you an example. So suppose that you have an algebra which is finite dimensional algebra, and suppose that it's of finite global dimension. And let's assume also that when you mod out by the Jacobson radical, that the quotient is separable. So this is always the case if your base field is perfect. For example, characteristic 0. Okay. So if you have one of those, then Orlov proved that actually that this algebra, it's a geometric non-commutative scheme. So you will be able always to see it inside the category of perfect complexes on a certain scheme. It can be a huge scheme, can be complicated, but you can see it inside. So let me give a remark that emphasizes this. So for example, suppose that you have this quiver where you have two vertices and an arrow. Then whenever you have a quiver, you can construct the quiver algebra associated to it. So if you take the quiver algebra, this is just this algebra of matrices of this form. But this, which is pretty close to that one, which was giving me the projective line. But it turns out that this algebra here, it's actually not Morita equivalent to a DG category of this form with I being smooth and proper. Okay, so it's never of this form, but it sits inside among one of those. Okay, so this is the kind of non-commutative objects that I'm interested in. They are close to commutative ones, but still they are, still more interesting than just the commutative ones. And now what's the goal of this non-commutative geometry is that if I give you any DG category, or if you want any geometric non-commutative scheme, you want to do geometry in these guys. For example, in this kind of algebras, I wanted to do the same thing with these objects. So if I want to do the same thing, I want to, in particular, to define L functions for these guys. So if I want to define L functions, I need some kind of cohomology theory. So I can define a non-commutative L-adic cohomology theory for these objects. And goes as follows. So you have you are working over a field, and suppose that you have a prime number L different from the characteristic of the field. You make that choice. Then you can consider something called the L-adic étal K theory. So this is defined on all DG categories over that base, and it goes with values in spectra. And if you have a DG category, what you can do is that you take the K theory of A with coefficients in Z mod Ln, and then do something which is called a Bose-field localization with respect to complex K theory, Ku. And so you get this spectrum, and then you do this completion. You do this homotopy limit on N, and you get this spectrum. So it's a machine that produces, given a DG category, produces a spectrum. And using it, one can define the L-adic cohomology. So you can define an even version. And what you do, you start with this L-adic K theory, not of A, but you base change to make it geometric. You base change to the separable closure, and you take this L-adic étal K theory. So you have the spectrum. You take the pi naught of this. So this is going to be a module over the L-adic integers, and then you invert L. If you invert L, then you get a vector space over the QL. Okay, and then you can do the same story here in the odd case. So where you take pi 1 of this spectrum, you base change to the separable closure, and then invert L. And these objects that you get here, they are actually these ones. These are QL linear modules over the absolute Galois group. So by definition, since I'm base changing to K bar, this carries an action of this absolute Galois group. So they are modules over this. Okay, so this is the idea to somehow make sense about L-adic cohomology theory in this generality, is that you really use K theory. And now using this, we can define the the non-commutative L functions. So here we are over a global field, and we consider a geometric non-commutative scheme. Okay, and then I can define, so can try to do the analog, the non-commutative analog of Serre's definition. You define the even L function. So again, you do a product over all places of your global field, and then you need to take these factors into account. You do the same story in the odd case. So this you define similarly, replacing even by odd. And how do you define these factors? Well, you do something similar. So you have now you have this even cohomology. So you again you base change to this completion. Here you consider the things that are fixed under inertia. So if they are fixed under inertia, here the geometric Frobenius will act, and you want to take characteristic polynomials. So you need to pass to C coefficients. So you need to do this base change here and here. Okay, now I have this automorphism of this C vector space, of this finite dimensional C vector space. And I take, so here it's my cardinality, I take minus S, and then I do the identity minus this and the determinant. Okay, so similarly with Serre's construction. And again, you can also do an odd version, okay, by replacing even by odd. And now, so we have these L functions defined for these gadgets. So what's the first theorem? So finally, the first theorem is the following. So is that if you consider these L functions, so the even and the odd case, they actually converge absolutely in a certain half plane. So in this case, when the real part of S is greater than 1, and here when the real part of S is greater than 3/2. So it's the non-commutative version of this convergence result of Serre. So if you want to draw these functions, you can say, well, you have two of them, and then you have so well, we have here this one. Oops, sorry. So I have this one here, here, and so they are well defined in this half plane region. So I recall that defined by this infinite product. This infinite product converges in this half plane region where here it's 1, here it's 1, here it's 0, and this one also. It's well defined here where this is 3/2 and this is 0. And then what is the non-commutative generalized Riemann hypothesis, which, well, there are two versions. There is the even version and the odd version. So it says, as you expect, that when you take the even L function, if it has a 0, or the odd L function, it has a 0 in this critical stripe, which means that the 0, that the complex variable is between 0 and 1, or between 1 and 3/2, sorry. Then this implies that actually the real part is equal to 1/2, the real part is equal to 1. So if you want, again, geometrically, this is saying, well, that in this region, I have the zeros need necessarily to be here. In this region, they necessarily need to be here, where here it's 1/2. So if you want, here it's 1/2, 1/2, and here it's 1. Okay. So you can actually phrase this version of the conjecture. Now, why is it useful? So this is the next result. Is useful by the following result. So it says the following. So suppose that you have your favorite algebraic variety. So you have your favorite smooth proper K-scheme. Then there are two things you can do. You can look at this generalized Riemann hypothesis for X, and you can consider it, for example, those where the W is even, or you can consider the non-commutative version of your Riemann hypothesis for the DG category associated to X. And similarly, you can do the odd version. So you can consider this for odd, and you can consider this for odd. Okay, and then what turns out is that, well, if the commutative, so if the generalized Riemann hypothesis holds, then the non-commutative version also holds, but also the converse. So the converse also holds. So in certain cases, so when you are in positive characteristic, you also have the converse implication. Or if you are in characteristic 0, when these L functions that you are considering, they actually satisfy this condition C2. So they are supposed to satisfy this condition C2. So morally speaking, this result is just telling you that, well, you have this conjecture defined for schemes, for algebraic varieties. You can define it in much more generality in such a way that when you plug it in this particular case of DG categories that come from schemes, you recover the original conjecture. So you are actually generalizing the conjecture from commutative role to the non-commutative role. Okay. So now, why is this useful? So there are several applications. For the lack of time, let me just mention one application to commutative geometry and one to non-commutative geometry. So an application to commutative geometry. So, of course, we are over a global field. And since we know that in geometry, in the case of in positive characteristic, the conjecture was proven by Deligne and Grothendieck, so let's restrict ourselves to the case of characteristic 0. And then what's interesting here is that sometimes in the literature, or very often in the literature, you can find two algebraic varieties that are geometrically very different, but their derived categories actually they share, there is a strong relation between the derived categories. They are very different geometrically, but the derived categories are pretty close. And so using this approach, you can actually relate the original conjectures from these two algebraic varieties, because you first consider the non-commutative versions, use them to relate the conjecture, but the non-commutative versions and the commutative versions of the conjectures are equivalent. So you relate them using non-commutative geometry. So there are lots of techniques in the literature to relate derived categories. Let me just mention one of them. Is something called homological projective duality. So usually written by HPD. So HPD. So this was a technique developed by Kuznetsov in order to study linear sections of algebraic varieties. So you have, the setting is the following. You have an algebraic variety equipped with a map towards a projective space, F. Then let's write by O of 1 the line bundle that you get by pulling back the line bundle on P0. And then, so I'm interested now in taking linear sections. Suppose that F is actually inside the projective space and then I have an hyperplane. So I want to intersect X with this hyperplane and do this cut and get a new algebraic variety. So if I want to do that, I can study all these linear sections simultaneously. So I can first consider the incidence quadrant. So which is defined, so you have the inside the projective space with its dual. So you can identify a point in the dual projective space as an hyperplane in the projective space. So you can look at this intercept incidence quadrant, and you can look at this universal hyperplane section. So which is defined, so let's call it H, which is defined as this fiber product of X with this incidence quadrant over the projective space, and this sits inside X cross the dual projective space. And now the point is that suppose that we know something about this category of X, of my variety. Suppose that it actually admits something that is called Lefschetz decomposition. So admits what is called a Lefschetz decomposition. So this means that you actually have a nested sequence of triangulated categories, such that when you twist them using this line bundle here, you get actually a semi-orthogonal decomposition. So you have a bunch of categories inside your category that generate the entire category, and there are no X in one dimension. So it's somehow the category of perfect complexes on X is glued out of these ones by a certain glue given by modules. Okay. And now if this happens, if you are in this situation, then we can say something about the perfect complexes of this hyperplane section. That's what I'm interested in. So it comes with this part of my, so this piece exists also here. So also here, but then you see H, calligraphic H is on X cross the dual projective space. So here you can do box times the perfect complexes of the dual projective space. And then it turns out that then you have an orthogonal that sits there, which is something mysterious. It's just a category here, which is called the HP dual category of X. So you start with something very geometric and you end up with this thing in red, which is just a category, an abstract category, which is the orthogonal complement of these pieces. But what's interesting in this theory is that this category here, sometimes it turns out that it's geometric. It's coming from another algebraic variety, which is called the HP dual of X, which in particular comes equipped now with a map to the dual projective space. Okay, so these things actually exist in pairs. There is some kind of duality. And so what you can do is that whenever you have a subspace in here, you can take the linear section of your X. So this you define it as the fiber product over the projective space with the L orthogonal. And you can also define the other linear section where you do this fiber product over the dual projective space with PL. So you get two algebraic varieties given by linear sections, which are geometrically very different, can have very different dimensions, etc. But the drive categories, there is a very strong relation between them. In fact, they share a common piece, which is a non-commutative piece. And then all the other pieces are somehow more or less trivial. So using this and using the previous results, we can say the following. So suppose that these linear sections are actually smooth. Suppose that they have the expected dimensions in the sense that the codimension of your linear section is equal to the dimension that you are using, and also for YL. And also suppose that the largest subcategory here, the A0, the largest one actually admits a full exceptional collection, full exceptional collection. So these are the assumptions. Let me just say that, well, the first two, all of them are quite mild. The first two holds for any generic choice of L. So if you change L slightly, you'll have them. And the last one holds in all the examples in the literature. So they are quite mild. But under these assumptions, what happens is that the extended Riemann hypothesis for this base field that I'm working in actually implies that the generalized Riemann hypothesis for one section, and here I'm using just the even part, and the generalized Riemann hypothesis for the other section, again I'm using the even part, they are actually equivalent. And in what regards the odd part of these linear sections here, they are actually equivalent. So this result is saying that actually the conjecture, the classical one, the generalized Riemann hypothesis, is invariant under HPD duality. So this is helpful in the sense that cuts in half the difficulty of proving the conjecture. If you are able to prove it for one, you'll get the proof for the other for free. Of course, we don't know the proof in any case, so no cases are known, but this is telling you that, well, if it's true for one, automatically you'll get for the other. So this is establishing a very strong relation between this, between the conjectures for varieties which are very different geometrically. Okay, so this is an application, and let me just say that, well, there are many HPD dualities in the literature. For example, the Veronese-Clifford duality, the Grassmannian Pfaffian duality, the Spinor duality, the determinantal duality, etc. So in many cases where you actually have this strong link between the generalized Riemann hypothesis for two things which are quite different geometrically. Okay, so this is one possible application in geometry, in commutative geometry. Let me just finish with an application to non-commutative geometry. So here I'm working over a global field, no restrictions on the cardinality, on the characteristic, and so let's think about these finite dimensional algebras, which are required to be of finite global dimension, and also I require that the quotient by the Jacobson radical to be separable. So this is true whenever the base field is perfect, for example, characteristic 0. So what can we say in this case about the conjecture? So first of all, we can look at the simple modules. So this is a semi-simple algebra. I can look at the corresponding simple modules. And then I can look at the endomorphisms of each one of them over A over J. So if I do this, A over J, so what I get, it's division algebras, division K algebras. So they are algebras over the base K. And then I can look at the center of these algebras. And the center of these algebras in this case is going to be actually a separable field extension, a finite separable field extension. So these things are separable field extensions. So, separable field extension. And then the result is the following, is that if I'm interested in proving this conjecture for my algebra, for my original algebra, it actually follows from these conjectures for this spec of each one of these separable field extensions, where here, where here I'm going from 0, sorry, I'm going from 1 to n. And this implies this. So if the conjectures hold for these separable finite field extensions, then you also have the conjecture for A. And the odd case, well, the odd case, it holds always. So this is not complicated. So you get as a corollary, maybe that's the upshot, is that the conjecture, this conjecture for A, and also the odd version, so they actually holds when you are in positive characteristic, because there you know that the generalized Riemann hypothesis is true. So you know that for this kind of algebras here, the non-commutative generalized Riemann hypothesis is true. Okay. And maybe a remark is that, well, what can we say about these conjectures for these separable field extensions? Well, they already exist in the literature, because when you take these L functions in here, for each one of them, well, these L functions are actually the Artin L functions. So this is the Artin L function of this representation of the absolute Galois group that is going to act on C, and here you have spec Ki, and then you do the separable closure and you are done. So you know that you have this Grothendieck-Galois correspondence between these separable field extensions and these finite sets equipped with this action of the continuous action of this Galois group. So you have this finite dimensional C representation, and it's the Artin L function of this representation that it's giving you the L function that you are using in this conjecture. So it's something that it's already there in the literature. And maybe a very final remark is that everything above, it can be generalized. There's a generalization to actually finite dimensional DG algebra. So there's a differential graded version of the above, where you also have a proof of this non-commutative generalized Riemann hypothesis. Okay, so I think my time is up, and I think this already gives you an idea of for what I wanted to explain to you guys. Okay, thank you for your time.
Okay, thank you for a very nice talk. Open up other questions. Just unmute yourselves, or if you prefer, you can just give the question in the chat and I can read it out.
I have a question on the construction of the L-adic homology. So you use pi 0 and pi 1. So how about the higher homotopy groups? Are they isomorphic to the pi 0 or pi 1?
That is known in the case of a scheme, but not known in general.
I see.
Yeah, because this then in order to prove this theorem here, this theorem here, what you are going to use actually is the relation between when you plug your non-commutative L-adic homology to this category of perfect complexes. And then you need to relate it with the classical L-adic homology of X. And if you use pi 0 and pi 1, then you have a relation where the weights are the ones that I want. If you use another, for example, if you change from pi 0 to pi 2, you would have a correspondence where the weights are shifted. So in the point of view of commutative varieties, nothing changes, but in the case of non-commutative varieties, yeah, it's not known.
By the way, this construction, are they invariant and Morita equivalence between DG categories?
Yes. Because yes, everything is Morita invariant. Whenever you take K-theory, here you are just using a fancy version of K-theory. And going to the separable closure, also again, you preserve Morita equivalence. And it has other properties. For example, whenever you have a short-exact sequence of DG categories, which is something which is called like a Drinfeld short-exact sequence. Then if you apply this invariant, you get a long exact sequence, so like in topology, if you want.
Okay, so are there other questions?
I have a very off-topic question. What application were you using to present? It looked fantastic. Just curious.
Sorry, what's the question?
What software were you using to present your lecture? It just looked very good. That's what I'm saying.
I don't know. Is this stuff notes? Notes, and
Okay.
then I simply changed my background to being black. I think
Okay.
nothing else.
No. Thank you.
Okay, so well, I have a question, and the Lefschetz decomposition that you were describing there, I mean, can this be understood somehow as a generalization of Lefschetz decomposition on a projective variety or a Kähler manifold?
No, this is the generalization. Where is it? It's the generalization of this construction of Bailinson. So first of all, where is it?
Or I guess my question is, why is it called Lefschetz decomposition?
Yeah, I mean, it's, yeah. So let's say, first of all, you have this semi-orthogonal decomposition, which is a notion that exists. And Lefschetz decomposition is a particular case. A particular case where you start with categories that are nested, one bigger than the other, so you have a filtration. And then you are twisting them using this invertible object that you have. Okay. And to get your semi-orthogonal decomposition. And the main example, I mean, the baby example is this thing of Bailinson, which is if you take the projective space, if you take Pn and you take the perfect complexes on Pn, then you would get O, O1, O2 until O(n minus 1). So here in this case, these categories will be always the same and will be just the categories of your base field. And then you're just twisting them n times if you want. 1 time, 2 times, etc.
And you're twisting by line bundles.
By a line bundle, yeah. So you have this invertible object in your category, which you use to twist the category. Yeah, it's the objects which are tensored by that one. And this is the main example, and then you go from there. Yeah.
Okay.
So it's just and so maybe my point is that maybe here it was not so clear because I didn't have time to talk about this kind of examples. But the main point here is that if you have these two things which are geometrically unrelated, but when you look at these categories, they somehow break up into a piece where it's a mysterious piece and then something else. Again, this breaks out into the same piece and then something else. So you really to relate them, you need to use this non-commutative piece. So in order to relate two geometric things, you use this non-commutative category. So you really need to have a formalism where you can talk about everything in the non-commutative setting so that you can talk about the non-commutative conjecture for this C, which is a mysterious, it's like this C here. It's just an orthogonal complement, okay? The other pieces are geometric, but this is what's left over. It's there, it's just a category. So if you have the formalism to talk about the conjecture for that piece, then you can do this this somehow zigzag. You start with two geometric things, you go to non-commutative geometry and then come back. So this is like the main idea of the talk that I want to.
Very nice.
Are you able to prove the conjecture for the non-commutative K3 surfaces? Or?
Yeah, that's a good question. I mean, it's there is a relation. Yeah, so you're talking about this Kuznetsov component. Yeah, right. No, I don't know how to prove it. It's related to the. I mean, I think if it's true for your x, then it will be true for this component. But then, yeah, I don't know. I don't know how to prove it. But that's a very natural and interesting question. Yes, indeed.
Oh, by the way, I found that you have developed non-commutative wave conjecture and non-commutative Grothendieck standard conjecture. And are these all related with non-commutative?
Yeah, so the Weil conjecture, we are working over a finite field. Here, I'm not working over a finite field, I'm working over a global field. But it's related in the sense, like I was saying, so for example, if you are over if your global field is of a positive characteristic, so if your field is of positive characteristic, then it's actually the function field of a curve. And then, so what, as I was saying, what the link said is that, well, the L function for this for x defined over that curve over this field, you can see that as the L function for a certain L-adic sheaf on the curve. And then if you specify, you can go to a finite field because it's a curve over a finite field. So yeah, they are related, the Weil conjecture and the Riemann, but yeah. Yeah, that's one possible relation.
I have an extremely naive question, but if you're looking at let's say Q-deformed homogeneous coordinate rings, and you take them at Q or root of unity, what happens in that case? I mean, because the root of unity corresponding to finite fields in a very rough sense. I wonder if you look here at roots of unity.
Yeah, I don't know what to say. It's a bit far from what I'm used to think about. So you are thinking some kind of, in terms of some kind of F1 procedure? Like...
No, I mean, if you look at quantum groups over roots of unity, then the representation theory looks like Lie theory over finite fields. Mm-hmm. There's this rough idea that like quantum groups at roots of unity correspond to geometry over finite fields. So I just wonder if you input into this machinery something at roots of unity, does the Riemann hypothesis start to look like something over finite fields?
Yeah, I don't know. That's a good question. I mean, here I can only phrase it for, as I said, I can only phrase it for this kind of non-commutative, these geometric non-commutative schemes. So I don't know if the example that you are suggesting actually is one of those that you can see it inside.
But suppose you take just the quantum plane, the usual quantum plane.
Yes.
And the Q that you have here is then a root of unity.
Yes. So yeah, I think in those particular examples, I don't remember, but I had the feeling that you always have some kind of semi-orthogonal decomposition in that case. So if you have a semi-orthogonal decomposition, then you are more or less done, because somehow all this machinery, one way to see it is that there is a theory of non-commutative motives, which is some kind of universal invariant. So all this machinery that you are using is, so this non-commutative L-adic homology, etc., factors through that non-commutative motives. And whenever you have a semi-orthogonal decomposition, the associated non-commutative motives will be just a bunch of points. So you lose completely the extensions. So a full exceptional collection is just, you have these exceptional objects, there are no morphisms in one direction, and there are only morphisms in one direction. So you are gluing these points, but this gluing disappears. Somehow it's like here, the gluing disappears because you only see this piece and this piece when you go down, because it's like K0. When you do K0 of anything, whenever you have a triangle, you can have these two kinds of triangle. And you see in K theory, this guy, the class of this guy will be the sum of A plus C, and the class of B will be the sum of A plus C. So the K0 doesn't see triangles, they treat them all as the same. Mm-hmm. So somehow the extensions disappear when you go to K0. So that's basically what K0 does, the Grothendieck group. So he only sees the end, A and C, doesn't see the middle. And so whenever you have a full exceptional collection, it's the same procedure. The glue, so which is an extension, somehow disappears. You don't see it. So in terms of the L function, it will be just the L function of the points. So somehow you are reduced to points. So morally speaking, you are reduced to the Riemann hypothesis.
Okay, thank you.
If I remember correctly about the quantum planes, yeah.
Okay, so do we have any more questions?
Maybe I will ask one question, right? So the class of L functions which appear.
Sorry, I'm not hearing very well.
Okay, so is it better? I mean, I don't have camera, just microphone. I'm not sure.
I think it's better now.
Okay, it's better. So I have a very naive question. So the class of L functions which appeared in your talk, how is it related to classical automorphic L functions?
Yeah, that's a good question. I don't know. Yeah, it's a good question. If they
and what was the implication for the structure of your category for the non-commutative object? So
yeah, with one application, if you are able to prove that this L function
equal,
you would have something like meromorphic continuation and things like
that. Sure.
But yeah, it's a very natural and interesting question. I don't know what to say. Yeah.
And by the way, did you try? So is it manageable to do something like the kind of Mellin transform on your L function?
I have not tried. Yeah, that's something that I'm planning to do in the future. Yeah, that's again another very natural thing. Yeah.
Okay. And by the way, so if I have I'm here and asking. So is there something like, or I'm asking about classical automorphic function, but is in this somewhat situation or it's something like a non-commutative version of locally symmetric space or locally symmetric spaces? Are there? I mean like kind of non-commutative algebra and some kind of discrete group action acting on it by some sort of.
Yeah, I mean, I don't know.
Okay.
Yeah.
Because I'm not sure whether the right question is to look at classical automorphic functions or whether you should try to manufacture some kind of locally symmetric space of non-commutative type coming from, well, from something, I don't know from what, but and some discrete subgroup of acting on it by automorphism, or I don't know, some kind of.
Yeah, it's interesting.
Okay.
No, yeah, it's definitely interesting. I don't know. I mean.
Okay. Yeah. Good. Very good. Okay.
Yeah.
Have you considered to construct a similar thing over fields with one element, F1? Or?
Yeah, that's always always difficult to know where to start. What's the correct formalism for F1, right? I don't know. No, I've not considered it. No, that's yeah, another interesting thing. I don't know. Yeah, I don't know what to say. I mean,
Okay, so are there any more questions? There have been quite a few, so maybe this is a good point to stop. Okay, so we thank you again for a very nice talk. And so next week's talk, Karen, do you want to put up the next week? I think is Rita Fioresi. This will actually be in person now that these things are allowed again. Karen, do you have the title? No.
Yeah.
Okay, well, anyway, next week's talk will be by Rita Fioresi. I'm not too sure if we actually have a title yet, but yeah, we'll send out the email as usual as soon as we have. Oh, here we go. So it's Rita Fioresi from the University of Bologna speaking this day next week on quantum principal bundles over non-affine spaces. So you can find the abstract on the webpage. And that will be, again, a hybrid. So it will be in person and also broadcast on the internet. Okay, so yeah, thank you everybody for coming, and hopefully we'll see you next week.